Okay, all right, so here in this particular video, I have a few more MCQ practice for you to follow here. Here's the first one. If you need to, pause, read. Other than that, you have essentially three shapes that's allowed to roll with different radii. So it wants us to find the ratio of the maximum height for each of these ones, okay? So essentially, what this particular problem is saying is that there are three different objects moving horizontally, and it's going to eventually roll up the ramp and comes to a stop. So here's the visual for you, okay? I'm gonna take this visual away real quick. Initially, it's moving horizontally and it's rolling, so therefore it has to have two forms of energy, a KE linear and a KE rotational. And as it rolls up the ramp, it'll slow down and eventually come to a stop. All right, so it's going to reach some sort of maximum height at that point. So I'm gonna take the visual away for you. So I'm just gonna set up conservation energy. If you kept up initially on the flat horizontal surface, if there's friction, rolling without friction would imply that it's spinning, and therefore there's a KE rod, and then because it's moving, there's a KE linear, and eventually all that energy will be converted to potential energy due to gravity at some height. So I'm just gonna expand these two functions. KE rod is 1/2 I omega square. The KE linear is 1/2 mv square, and then I'm just gonna break up PE here into mgh. But here in my subscript, I just have max because, again, it's asking for us to compare the maximum height that they climb. All right. So I'm just gonna go ahead and break this stuff up into further stuff, just so I can isolate for h max, because essentially that's what it's asking us to do. So I here is generically c for the coefficient of shapes. That's allowed to roll, and then here's mr square. And then the KE linear term I kept as is, and then on the right side is kept as is, okay? So I'm just gonna go ahead and cross stuff out that I don't need. All three terms have an m, the mass of the shape, so I'm just gonna cancel that out. And then likewise here on the left side for KE rod, there's an r square, but here is the v over r, but the exponent will be distributed to the v. It will also be distributed to the r, which makes r on the bottom square. R square on the bottom will cancel out with r square on the top. So I'm just gonna cancel that r term there. I'll still square the v though, I just don't need to square the r because it will cancel out. So I'm just gonna clean that up a little bit. So it would just be 1/2 times c. That's the only thing that's left after I've canceled out m and r square. And then the v once again is squared because the exponent is outside. And the k linear is just 1/2 v squared now, or we gotta reduce to just 1/2 v squared, and the right side is just g and h max. All right, so here I'm just gonna isolate for h max by dividing both sides by c. So essentially I can factor out this 1/2 v squared because both of these terms on the left side has a 1/2 and a v squared. So I'm just gonna do that really quick, and then I'm just gonna keep the c because that hasn't been factored out yet. And then here you've already factored out 1/2 and v squared, so the second term is just a 1. So hopefully you kept up with the algebra there. All right, so just factor out like terms. And on the bottom is a g because the g on the right side is in the numerator. So I'm just gonna go ahead and move it to the bottom left denominator by dividing both sides by g. And here is, I think, where you can make this problem super easy to do, right? Well, the problem states that the speed at the center of mass at the bottom incline is the same for all of them. Well, I'm just gonna box this, and I can only do this because it's straight up said the velocity at the bottom is the same for all of these shapes. Well, g is the same for all of the shapes because it's acceleration due to gravity. So I'm just gonna ignore this, okay? I can ignore it because it's the same for all three objects. So be careful when you can apply this particular skill, okay? Once again, it says that v is the same for all three. G is the same for all three. So there's no need to multiply by this particular term on the outside, if they're all the same. So I'm just gonna go ahead and carry over this simplified version of h. So really I can think of h max as proportional to, 1 plus c. So I have an equal sign here, but really I'm just carrying my work over. It's not technically equal to, it's just proportional to 1 plus 1. So the first shape I'm gonna do is the ring. The c value for the ring is a 1, okay? So 1 plus 1 is just 2, right? And I can do the same skill really here for the solid cylinder. Well, the shape for the solid cylinder has a coefficient of 1/2. 1/2 plus 1 is just 1.5. And I want to do it again for the third shape, which is a solid sphere. Well, the coefficient for a solid sphere is 2/5, which is 0.4, right? 2 over 5 is 0.4 plus 1, which is 1.4, right? Now, once you get here, if you're looking at the answer choices, right, there's no 2, 1.5, or 1.4. So this is where you just kind of have to, be a little clever. All you have to do is multiply everything by 10, right? So if you take 2, multiply everything by 10, that will give you 20. 1.5 times 10, that will give you 15. 1.4 times 10, it will give you 14. So remember, it's a ratio problem. So as long as you multiply everything by the same value, it's okay. So here, why would I multiply by 10? Because I think if I scan the answer choices, you know, I can turn a 2, a 1.5, and a 1.4 into 20, 15, and 14 easily. So here, the answer in this particular order, the ring, the solid cylinder, and then the solid sphere is going to be 20 to 15 to 14, okay? Because I did the ring first, and it sets the ring first here in the ratio problem. All right. Other than that, that's it for this one. Here's the next one. Here we have a solid cylinder of mass, blah, 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 and it says 50 centimeters. The radius is 50 centimeters, and then the incline here is angle at 30 degrees, and it wants to find the distance that it traveled up the incline. So here, initially, it's moving horizontally at a speed of 4 meters per second. It's essentially going to climb up to the top. So similarly to the last one, okay? Here, the value is given though. So I'm just going to go ahead and call this H. I'm going to call this L. Essentially, L is in red here because that's what the question is asking us to find. It's just the distance traveled by the cylinder on the inclined surface. Okay, so as you do these problems, eventually, is it looking for height, or is it looking for the length of the ramp, the distance traveled along the surface of the ramp? Here, L is what we're looking for. So I'm just going to set up conservation energy again. Initially, you have an object rolling on a flat surface. It's going to climb. So similar to the last problem, I'm just going to go ahead and do this. I'm gonna go ahead and say that K linear plus K rod is equal to mgh. Well, I don't know what h is here, but I can find h, right? You're given an angle. So here I apply sine of theta is equal to opposite over hypotenuse. Opposite in this case is the height, and the hypotenuse is just the length of the ramp, which we're interested in. So I'm just gonna solve for h. I'm just gonna go ahead and introduce L into my function. You know, why not just get L into the function, because that's what it's asked us to do. So here, I can just solve for h by multiplying both sides by L, or I can just, L's on the bottom right here. I'm just going to move it to top left, so h is just L sine theta. So wherever h is, I'm just going to replace it with L sine theta. I added a few things here for you, right? The I value for this particular problem is a solid cylinder, so it's just 1/2 mr squared. And in omega, I'm going to break that up into v over r because the linear speed was given to me, right? So know when to get rid of omega, know when to get rid of v. Here I got rid of omega because omega wasn't given, the linear speed was given, and I know the relationship between omega and v is this particular expression here. All right, so here I'm just going to clean it up a little bit. M cancels out, and then the first term is just 1/2 v squared. The second term here is 1/4 because 1/2 times 1/2 is 1/4, and then r squared here is going to cancel with that. I distribute the exponent to the v squared here and the r squared here. So if you kept up the first problem, you know, r squared here in the second term, or the k rod term, is always going to cancel out. So I'm just going to clean this up. Now, I do want to point this out in case you do problems and you don't really pay attention to what's needed and what's not necessary, right? This particular problem gave you the mass of the cylinder, and it also gave you the radius of the cylinder. Well, if you think about it just a little bit, I've already canceled the mass term out in my work, which means that it does not depend on mass. And I just cancel all the r terms out in my work. So while the mass is given and the radius is given, you actually need to have big brain and go, well, I just cross out m. There's a reason why, because it's not needed or it's not important. And then I also cross out r, the radius of the shape. Why? Because it's also not needed. So I just made a really important point for you here, right? The height here is independent of m and r, the mass of the object and the radius of the object, and same with velocity. Okay, so keep these important concepts as you practice rotational dynamics. Sometimes though, well, the question will troll you by giving you excess information that you don't even need, and if you're a rookie, you might sit there and try to use all this information while you don't need to. All right, so I'm just going to clean my work up. A 1/2 it was 0.5, and then 1/4 is 0.25. So 0.5 plus 0.25 is 0.75, which is the same as 3/4. Or you can find common denominator here. The common denominator here would be 4, right? So you can make this 2 into a 4 by multiplying the bottom by 2, but also the top by 2. So 1 times 2 is 2, 2 plus 1 is 3, and then the common denominator is 4. Up to you, however you want to do algebra. But again, focus on L here. Essentially, that's what's being asked of you. So I'm just going to go ahead and isolate for L, dividing both sides by g and sine theta. Here, the v is v squared, just times 3. And then 4 is on the bottom, so I just rewrote it where it's a little nicer. So 3v squared, right? 3 times v squared over 4, and then the g sine theta, theta being 30 degrees because it's given. And then it says to take g as 10 in the problem, so I'm just going to use g as 10. So here v is 4, I just plug in the value, and then g is 10, and then sine of 30 is a half. You can punch on your calculator, or if you just know it based on unit circle. And really here it's just simplifying. There's a 4 square on top. I can cancel 1 to the 4s with the 4 on the bottom. So 1 to the 4 is going to cancel out. And so therefore 3 times 4 is 12. And then if I cancel out this 4, it would just be 10 times a half. 10 times a half is just 5. Or again, you can just use your calculator. It doesn't really matter to me. 12 divided by 5, that's going to give you 2.4. And that's the answer here. All right. So that's the length of the ramp. Or that's the distance traveled by this particular solid cylinder along the surface of the ramp. Now, I'm going to do the same problem though, using a different strategy. Again, there's different ways to get here, right? Same problem. However, I'm going to use kinematics. You know, I know that the acceleration for these types of problem is a constant. Because it's a constant, it allows me to use this kinematics equation. So if you're familiar with this from fundamental like kinematics, Vf squared minus Vi squared is equal to 2a delta x. Well, I know Vf is 0 because it says it comes to a stop. Well, Vi is given as 4 meters per second. But here, the important thing here is that A, if you know the function for A, which is in my other video. So once again, if you don't know this and this is your first video that you run into, watch my other one because I derived the function here for A. A is simply g sine theta over 1 plus c, where c is the coefficient of moment of inertia for this particular shape. And then x here is just L because the surface of the incline, the distance in which it travels along, that's your x distance. And here, this problem is just called L, okay? Just go with the variable given. All right, other than that, I'm just gonna plug in Vi as 4, and then G here, I plug in negative 10 because the object is moving up the ramp. So if I take that as my positive direction, I know it's slowing down, so acceleration due to gravity or acceleration in general is gonna point in the opposite direction. So if upward is positive, then downward is negative. That's why there's a negative sign there. But honestly, for this one, even if you forget the negative sign here, it's not gonna goof you over because you're not really adding anything. So here, it's up to you. If you know, you can be a little sloppy. If you don't know, just be careful with your signs, okay? So G, I'm just gonna use 10 because it says to use 10, and then sine of 30 degrees, and then once again, the coefficient for a solid cylinder here is just 1/2. Capital L is outside the parentheses, so I'm just gonna clean this up. The negative sign on the left, negative sign on the right is gonna cancel out. 4 squared is 16, and then 5 times sine of 30. Once again, sine of 30 is a half, so 10 times a half is 5. That's where the 5 comes from. And then 1 plus 1/2 is 3/2. I kept all this in fraction. But here you have a 5, and you're going to divide it by a fraction, which means you need to multiply by the reciprocal, which I'm going to do. So instead of saying dividing by 3/2, I'm just going to take the 5 and multiply by 2 over 3. Well, here it's just basic math, right? 2 times 5 times 2. 2 times 5 is 10. 10 times 2 is 20. And then the bottom is just 3. So if you do that, you can move the 3 to the top left. It'd be 16 times 3 is 48, and then the numerator here is 20. So to get rid of 20, you would just divide by 20. So if you do 48 divided by 20, you'll get 2.4 as well. All right, so it matches with the answer previously calculated using conservation energy. So here, if you know the acceleration function, you can use kinematics. That's entirely up to you. And this is just one of 2 methods. I think there's other ways to do it. Here is a good multiple choice question, I think, to really test to see if you comprehend independent versus dependent variable, right? So in the previous problems, I pointed out that to find H max for these types of rolling problem, or to find the velocity at the bottom of the ramp, it's mass independent and also radius independent. So I'm just going to start with this. Sometimes you might run into this particular function, which can be derived from using conservation of energy. Well, there's a 2gh over 1 plus I over mr squared. This is commonly floating out there. So as long as you know where to get it or how to derive it, good for you. If you don't, really, again, it just comes from setting up conservation energy. However, I like to point out that if you know your stuff, I generically is just cmr squared. Okay. Well, C varies between shapes. So this C can be anything like a 1, a 1/2, a 2/3, a 2/5, depending on the shapes that they give you. But I generically is cmr squared. Well, the mr squared on top and the mr squared on the bottom is going to cancel. So that's just going to leave you with C. So I like this particular expression a lot better than the first one because it's just 2gh over 1 plus C. And as you can see here, there's no mass in this particular function, and there's no r in this particular function. So I mean, for the second time here in this video, I'm just going to say that independent of mass, right? Your velocity is independent of m and the radius of the object. So they might trick you by saying, well, What if the mass is like, twice as massive? What happens to the velocity? It would still get to that same speed at the bottom. I'm not talking about time, I'm just talking about speed. They might troll you by saying, well, what if one shape is r and the other shape is like 4 times the radius? Which one will have the greater velocity at the bottom, or the same, or less than? Hopefully you pick the same, because if it's the same shape, it has the same c regardless of r, okay? So for this one, if you understand this particular red statement, independent of m and r, it wants us to find a velocity versus r graph. Well, your velocity is independent of r, which means regardless of what the radius is, if you're looking at the same shape, which in this case it is, it said a student rolls several hoops. The I value for hoop is just a 1. So it doesn't matter the size of the hoop, as long as it's the same type of shape being a hoop. All the C's are 1, right? So therefore, it doesn't matter. Your velocity is independent of r, meaning as r increases, v stays the same, because it does not depend on it. It doesn't change. So answer B would be your best choice, okay? When things don't change, you get a horizontal line. I think this type of multiple choice question really tests to see if you understand whether a function is dependent or independent of certain variables, all right? So pay attention to stuff when you cancel stuff out in physics. Here's the last one for this one. Here, it wants us to find the tension in the string. So here you have a hanging mass, and you have some sort of cylinder here that's going to start spinning on an axis. And here are your choices, A, B, C, D, E. So here I'm just going to go ahead and attack it by setting up my f of g for the hanging mass. There's a tension in the string. This one, there's only one string on the right side of this particular solid disk. All right, so for the hanging mass, tension points upward because it acts against the hanging mass's motion. However, the force that is going to cause the solid disk to rotate is the same tension. So tension behaves differently based on which objects you're looking at here. It's actually going to cause this disk to rotate in the, clockwise direction. All right, so I'm just going to go ahead and set up my linear and rotational physics. Essentially, that's the big connection here. So I'm just going to do linear by focusing on the hanging mass, because the hanging mass is just moving downward. So that's linear, while the solid disk is going to be spinning. So if I set up Newton's second law, net force equals ma, I can identify that the weight, or the force of gravity for the hanging mass, is greater than tension. So I'm just going to do big minus small. So f of g here minus t is going to equal to ma for the hanging mass. And then for the right side of the work, for the rotation, well, the object that's going to be rotating is the solid disk. So for the solid disk, I know that there's a t that's going to act on this disk, which is going to cause it to rotate, which means there's a torque generated. So here in my work, I wrote the 2 torque function out for you. So torque is F perpendicular R, and then torque is also I times the angular acceleration. And then I want to set these 2 functions equal to each other. And then here I can just replace F with T, because the force that's causing this particular solid disk to spin is the tension in the string. R is just whatever R is in this diagram, and it gives us capital R, so I'll just use capital R. On the right side, the I value of a solid disk is just 1/2 mr squared. And alpha can be swapped out for A tan over R, right? The relationship between A tan is equal to R alpha. So if you're looking for alpha, you just divide both sides by R, and that's where this comes from. So here, one of the R's is going to cancel out. Here's the R on the left side, but there's an R squared in the numerator, so one of this R is going to cancel out that. But if you do that, you have an R left still. That leftover R is going to cancel with this R on the bottom. Or you can also think like, you see this R that I just put a line over? If you physically move that R, it would have to go to the bottom right. So there's an R already on the bottom. So R times R is going to give you R squared, which is going to cancel with the R squared on top. Okay, however you want to do it. So anyways, R is going to cancel out. So here's the tension. The tension here is going to be 1/2 ma tangent, or the tangential acceleration. So the weight is going to accelerate downward, but it touches the point on the outside of the solid disk, which is tangent, to the radius here, or to the axis of rotation there. So now that I have an expression for t, I can substitute in for t here in my work. Well, excuse me, I don't need to solve for 2 for t, excuse me. I need to solve for a. I'm looking for t, okay? So here in my work, I'm just going to take it a step farther. I'm actually going to solve for a, excuse me. I'm so used to solving for a. But this particular question asks you to solve for t, so I need to keep t. So to get a by itself, I'm just going to multiply both sides by 2, and at the same time divide both sides by m. So a here is going to equal to 2t over m. So here in my work, this is a tan, or a tangent, but a tangent is the same as a over here. I just didn't use the subscript tan here because, again, I think it's common sense to say that the weight is hanging on the outside of the solid disk was just tangent to the object's motion. All right, so I'm just going to substitute a out. because again, I'm trying to find t. So here on the left side, I haven't done anything. Wherever a is, I'm just going to plug in 2t over m, because that's just what I found a to be. Here I have a t on the left side, I have a t on the right side, so I'm going to combine like terms. So this negative t, I'm just going to move it to the right side by adding it. So really nothing has changed. I just rewrote, this is 2t times m, right? When you multiply it, it doesn't really matter. I just like the coefficient in the front. Here's the big M is still on the bottom. Again, this negative t, I just move it to the right, which makes it positive t. So now that you have this is you have a fraction here while you have a whole t here. So I'm just going to multiply this t by m over m, or big M over big M, just to get the common denominator, right? So you have a fraction that has a capital M on the bottom. So when you add fractions, you have to have common denominator. So I'm just going to multiply once again this capital T by M, but also divided by M, because it will cancel as 1. So really, again, you're just making visually more attractive by having a common denominator here. So here I'm just going to factor out the t. Both the terms in the numerator has a t, so I'm just going to factor that out. So the only thing left in the numerator, once I factor out the t for this term, is just 2m. That's where the 2m comes from. And then I factor out this t, so on the numerator it's just m. Well, here really it's just algebra. Okay, there's a good amount of algebra involved here. Here you have an m and an m, which you can factor out, right? So both these terms sits over a common denominator. So I'm going to factor out this capital M on the bottom, and I'm just going to move it to the top left, and that's where my work is. Okay, so all of a sudden you see a little m times g, and there's a big M, because now these two terms in the parentheses sits over a common variable capital M, which I can factor out, and I can also multiply that by both sides to get rid of it. And then the only thing left is 2 little m plus capital M in the numerator. But to get t by itself, I would need to divide by that term. So if you need to, pause and do this algebra on your paper just so you're good at it, right? The physics is done. This is just all algebra stuff. Now here, you notice this doesn't quite match any of the answer choices. So I had to take a little step further, okay? I'm going to divide the numerator by 2, but what you do on top, you have to do on the bottom, just so that I can find the answer to match one of these answer choices. So it'd be mg big M. I'm going to divide that by 2. If I do that, once again, you have to make sure your algebra is consistent. You got to do that for every term. So both terms on the bottom, I divided by 2 as well. The 2 there is going to cancel out. Okay. So essentially, if you look at it, you have mg times m over 2, and it matches with this particular here. Look at m, capital M, times little m times g over 2. And on the bottom, you have little m plus m, or big M, over 2. And the only answer choice that mirrors this format is this particular answer choice D, right? So while I have m, little m plus m over 2, they have a capital M over 2 plus m. It doesn't really matter, right? It's like 2 plus 3, 3 plus 2, it doesn't really matter. But anyways, the point is that it matches with answer choice D. So there's a lot of manipulation just to get it to look like that. All right, I hope that helps. Stay nerdy. Don't be wired.